Hi everyone, it's time for section 3.5, implicit differentiation. Okay, so at this point we have learned all of the derivative rules, ending with 3.4 and the chain rule. So where do we turn now? So this section is devoted to finding derivatives of non-functions, which seems like a pretty radical idea. Everything we've taken a derivative of so far has been a function. So we're going to see how this can apply to non-functions. And it ends up with this name, implicit differentiation. Let's see what that's all about to begin. So it turns out there are these two types of equations: explicit equations and implicit equations. We usually don't use that kind of language. But let me tell you, these are actually very familiar to us. So we'll start with the explicit equation. An explicit equation means that it's been solved for y. So it's going to look something like y equals, and then some, expression in terms of x. If it's solved for y, well, that's a function. So you see there, solved for y, aka a function. It could be called f of x equals at that point. On the other hand, there are implicit equations. Well, an implicit equation is not solved for y. And we've seen lots of those, not in this course, but over the years. And so an implicit equation is not necessarily a function. Usually it's not one. Okay, let's take a look at a quick example of an implicit equation. Something that's not solved for y, and it could be something as simple as x squared plus y squared equals 25. Now maybe you're looking at that and perhaps you know what the graph of x squared plus y squared equals 25 would be. If not, I'll show it to you right now. I'm just gonna back up a little bit. Here it is. It would be the graph of a circle with a radius of 5 and centered at the origin. Okay. So there's x squared plus y squared equals 25. And yeah, from the graph we can certainly see this is not a function, right? It does not pass the vertical line test. And as you look at that, you notice that there are, of course, points on that circle. And each of those points would have a tangent line. So I've highlighted this point right there. And if I was to draw the tangent line, I erased it just a moment ago. So it would be the line just coming down, moving in the same direction as the circle, just grazing by. Right there, like so. And let's say, apologize if there's some loud noise in the background. Neighbor's home is under construction, something going on. Let's say that point is at 4, 3. Just to make things easy. 4, 3 would be on the circle, right? 4 squared plus 3 squared would give you 25, so that is a point on the circle. So what if we wanted to find the equation, or maybe even just start with the slope of that tangent line right there at 4, 3. How would we do it? Okay, so here are the steps to finding the derivative of an implicit equation. And we call it the process implicit differentiation. Okay, I'm trying to make some of these words a little bit easier to read for you there on the screen. They're coming up a little bit light, and I apologize for the shadows. To find dy over dx, 2 steps. Take the derivative of both sides with respect to x. So there'll be a left side, right? A left side and a right side. So we'll take the derivative of both sides with respect to x. Now, we've never thought of a derivative that way because we've always worked with functions. And so we never thought of doing it to both sides. But certainly you can, even if you had, y equals I don't know, I'll just make something up. How about y equals 3x squared? I don't know. If we took the derivative, you could say we're taking the derivative of both sides, right? We took the derivative of y, and we took the derivative of 3x squared. Now, usually we don't think of it that way, but it certainly makes sense to do that. Okay, once you take the derivative of both sides with respect to x, then step number 2, we're going to isolate dy over dx. Now, step number 2 doesn't really make very much sense at this point until we see an example. So let's get to that. And I think I've got it on the next page. So we're going to look at our same example, x squared plus y squared equals 25. And just give me one moment. Needed a smaller piece of paper here. Okay. There we go. Looking back there, x squared plus y squared equals 25. So we'll start with step number 1. We're going to take the derivative of both sides with respect to x. And so for now, I'm simply going to write this. D over dx applied to the left, and d over dx applied to the right. So I'm indicating I'm about to take the derivative of the left side, and I'm about to take the derivative of the right side, and of course, these would still be equal. How is this going to work? Okay, let me show you. Well, let's start with the left side. The derivative of x squared, well, nothing unusual about that. That's going to be 2x. Over here on the right side, the derivative of 25, well, derivative of a constant, nothing unusual. That's going to be 0. The new piece, and what you're going to have to wrap your head around, what's different about this section than what came before, is going to be the derivative of the y squared. That's going to be a little bit funky. Let me just show you how it works out, and I'll explain each part. So the derivative of x squared, of course, is the 2x. Plus, how do we take the derivative of the y squared? Well, you see it right there, but let me explain where that comes from. So you see it begins with 2y. Well, just like derivative of x squared is 2x, we begin the derivative of y squared in the same way. The 2 comes down, it drops to a first power, it's 2y. However, that's not the end of the derivative. We then need to multiply by dy over dx. Okay, pause on that. We're going to come back to that. I'm going to explain why that is very soon. Okay, equals, and on the right side, the derivative of 25 is 0. Okay, so we see that. Okay, all those pieces make sense. So what's up with the 2y dy over dx? So I've got an explanation here. When we take the derivative of y squared with respect to x, we have to think of it as a chain rule. Why do we have to think of it as a chain rule? Because it's not the variable x here, it's a variable y. If it's the variable x, then it's the same derivative that we know and love, right? Just 2x. But when it's a variable other than this one, then we've got to think there's something else happening here. There's a chain rule. We think of the squared as the outside, and we think of the y as an inside function. Why would we have to think of the y as an inside function? Because y, we don't see it written here, but that is an expression of x. Just like the sort of things that we saw when we dealt with the chain rule. This takes a little bit of time to sink in. Why the y would be an inside function, but just know that is an expression of x. We just don't see it written there. So when we go to do the derivative, we've got to follow the chain rule. So we take the derivative of the outside first, the 2 comes down, it drops to a first power, and we repeat the y right there. So 2y to the first. But that's only the derivative of the outside. It's only the derivative of the squared. We then have to multiply by the derivative of the inside. Well, what is the derivative of the inside? Well, if all we see is y, then the derivative of y we simply write as dy over dx. And so 2y to the first times dy over dx, that's what we've got right there. A lot of times after I explain this, students are still kind of wrestling with it. I don't want to over-explain because that can lead to some confusion, but maybe I can go a little bit further. We could do something similar if we were using x squared. We could do a chain rule here, even though we wouldn't typically think of this as a chain rule. You could think of the squared as the outside and the x itself as the inside. Well, how would that work? Well, the derivative of the outside would be 2x to the first times, hey, what's the derivative of the inside? What's the derivative of just x? Well, you could say that's just 1. And so multiplying by 1 doesn't actually change anything. You still get 2x. So in the same way, you can treat y squared, except now when you take the derivative of y with respect to x, it's not 1. We write dy over dx, the derivative of y with respect to x. Okay. I'm sure that's still not satisfying to a lot of people. I'm sure it's still a strange concept. It always is whenever we teach this. What do you have to take away? Like, at the end of the day, what do you need to know? That's a good point to make. Whenever you take the derivative of y, do it normally, but then at the end, attach a dy over dx. Multiply that on the end to account for the chain rule. Bottom line. Okay, let's move on. So at this point, we've taken the derivative of both sides with respect to x. Now it's time for step number 2. We want to isolate the dy over dx. So how are we going to do that? We're going to subtract the 2x. Then we're going to divide by 2y. And there we have dy over dx isolated. When we divide by that, right, the 2's cancel. We get negative x over y as our derivative. And you notice something unusual here. That derivative function involves both the variable x and the variable y. And yes, that will very often, if not always, be the case when you're taking the derivative of an implicit equation. Your dy over dx will involve both the x variable and the y variable. Now, if we consider that, for the specific point that I marked on that circle, right, the point 43, what is that going to imply? What's the slope of the tangent line at the point 43? Well, you notice the point 43 has an x-coordinate and a y-coordinate. So when we're dealing with implicit derivatives, we'll need to plug in both x and y right there. We don't just plug in the x value like we would normally. So no problem. At the point 43, well, x is 4, y is 3. The slope of the tangent line there is negative 4/3. And if I go back to the drawing, hopefully that makes sense. Yeah, well, it's definitely a negative slope. And it's going down faster than its run, so it's dropping faster than it moves over, which I think you can kind of tell that in my picture, negative 4/3 slope. Hey, while we're talking about the point 43, what if we wanted to find the slope of the tangent line down here, the point directly beneath? What point is that? That'd be 4, negative 3. And that would have this slope, right? Or that's the line, actually. What if we wanted to find the slope of the tangent line at 4, negative 3? I don't know if I actually did this in my notes. Oh, I did. Oh, wow. Now, what is that slope? What's the slope at 4, negative 3? Well, same idea. Plug in your x, plug in your y. But now we've got 2 negatives, so they cancel out. We'd have dy over dx equals negative 4 over negative 3, and that would come out to positive 4/3. And that makes sense. Right? It's the negative version of the same slope, or the positive version of the same slope, you could say. 4/3. Okay. Many more examples we're going to dive into. I think that's enough for this video. See you in the next one.